Okay, and so for the last time, biomechanics of injury and prevention, application of biomechanics to injury prevention. And as ever, thanks both to Gian and Dr. Chitendra for making all this happen. And so we've covered, hopefully in a comprehensive detail, given the time frame that we've had to operate within, a series of key elements of the musculoskeletal system and generally biomechanics as a whole in relation to the body. Yesterday, we looked at some of the new and emerging techniques that are being used in orthopedic surgery to prevent and manage injury. Perhaps one of the other areas that's quite topical at the minute as well, probably more so in the Western world than it is here in the Eastern element of the world, but there's no reason why new and novel concepts and ideas from here can't contribute absolutely to those problems. And so we'll talk about some of the work that we're doing, how that involves topology optimization, which is techniques that I know IoT Ropar have interest in. And then we will show some of the work that we're doing at Cardiff to try and wrap it all up. And so we look at head predominantly protection as one of our main areas of research, and that is quite topical. These are newspapers from the UK, and they show the consequence of serious head injury in sport. And this was a Formula One driver whose car crashed into a stationary object, and he had a single severe impact that ultimately proved fatal. Michael Schumacher, again a Formula One driver, he had what we believe to be a severe impact while skiing. And his condition, whilst formally unknown, is believed to be life-changing as a consequence of what we understand was a single severe impact. Closer to home, both geographically in terms of the sporting context, Philip Hughes was a batsman for Australia, and he was struck by a ball whilst batting. It hit a part of his head that wasn't protected by the existing solutions, and it caused him a fatal injury as well. And so there are a series of selected examples where a single severe impact can cause near instantaneous severe injury. And that's appreciated, that's recognized, and to a certain extent you accept that risk when you go into any of these activities. To be struck on the head with a cricket ball is not hugely uncommon. To be killed by that strike is decidedly rare. If everyone had that outcome, then cricket would be forced to change injury. And so that's a consequence of a single severe head impact. And in all of these examples, there are reasonable solutions in place that prevent that. The cricketers wear their helmets, as do the Formula One drivers. And to the most part, they do a reasonably effective job because the vast majority of head impacts to a ball to the head aren't fatal. The player plays on. And in Formula One, when you're driving at the speeds that cars go, with the design constraints that have to exist reasonably to allow a driver to operate a car, then there comes a point where whatever engineering intervention you use just will not be effective enough to provide sufficient protection. There is, though, a different type of brain injury. There is a brain injury that relies on less severe energies that strike the head, and cricket, to a certain extent, is leading the way in this. You might have heard recently that they're introducing concussion substitutes. A concussion substitute is a player who gets struck by the ball, who doesn't have an injury as nearly as extreme and as severe as this, but has what is now recognized neurologically to be a subtle change in the brain structure that's temporary. But if a second collision or second blow was to happen to the same point of the head, then the cumulative effect of that original concussion can be really quite serious. And so there's long been not long been, but there's recently been an argument that when a concussion occurs, in whatever sporting context or indeed whatever environment of life at all, then the safest type of management is to withdraw that person from getting a repeated exposure to that risk. And so cricket now has concussion substitutes whereby if you get struck by the ball, you can be removed and swapped in for a new player. And that's a very recent and very significant change in international sport. And it follows on from these examples. We have American football that's probably leading the way in brain research at the minute. And I think for the sake of this presentation, it's important almost to remove the context of American football. Because if we start talking about American football here, or indeed in the UK, then there's not a huge amount of appetite for what happens in that game. It's not a game that's particularly closely followed in the UK, and I understand it's followed even less over here. But the key point from a biomechanics point of view is that they are leading the way in brain injury and protection. Again, rugby, not a hugely popular sport. I haven't seen a set of rugby posts in the week that I've been here, but we again want to try and take this out of the sport-specific context because they too recognize the importance of concussion, and they too have developed a strategy that tries to reduce the risk that their players are exposed to. As soon as there is a head collision, the player gets taken off the pitch and they have to do a pitch-side assessment. If they fail that pitch-side assessment, they get withdrawn from the game, a substitute's brought on, and that player has to follow a return-to-play protocol. Why? Because they recognize, and medics recognize now the consequence or the potential risk of a second concussion whilst you're still recovering from the first. The problem, however, is that diagnosing a concussion is really quite demanding, quite difficult, to the extent that the pitch-side concussion test at the minute is very much dependent on the medic and the player involved. There is no measure or threshold after which the scientific quantification of your condition exceeds a threshold and so you're withdrawn. It's very much a subjective process. And World Rugby, who manage the game, are continually trying to find an objective way of doing it, i.e. a way that takes the opinion of people out of it entirely. Basketball, not a game that you would immediately associate with concussion. They have problems with the sport as well. As does soccer, through heading a ball. And so there are suddenly many sports that not only recognize the significance of mitigating against one severe collision, and we can see here with American football, the protection they wear, it's hard to imagine how they could suffer a severe head injury blow because they have substantial helmets on. But the consequence of an accumulation of less severe injuries becomes quite real. In these sports, the risk is obvious. In this sport, the risk has only just become apparent. There was a Western film called Concussion that was based exclusively around the story of the emergence of head injuries in American football. And they find that despite wearing helmets, the helmets are designed specifically to mitigate against severe risk. And so the likelihood of getting a skull fracture playing American football is remote because you're wearing a helmet. And that's what all helmets really are designed to do. They're designed to prevent severe injury. And so those motorcyclists outside that choose to wear a helmet, if they fall off, then if the circumstance exposes them to a risk of severe injury, then hopefully by wearing the helmet, that won't happen. The helmet stops a severe blow, but it also stops a penetration as well. So if you fall off and happen to land on a sharp object, then the shell on the outside of your helmet is meant to stop that object from piercing it and thereby risk puncturing your skull. But these helmets, nor helmets outside worn by those on two wheels, are particularly good at protecting against this. And yet we know that this is becoming a problem. Have more than one of these, have an accumulation of these, and you suddenly become at risk of serious long-term injury. And so this is a new issue that sport in particular and life in general is starting to accept and having to manage. But how do we measure risk? You may or may not be aware of an abbreviated injury score. Now, an abbreviated injury score is effectively a mechanism of categorizing the severity of injury, and it's adopted from the automotive sector. And these are useful scales in whatever line of biomechanics that you work in. So from a head injury perspective, if a paper reports an abbreviated injury score of 1, you know they're dealing with concussion. And you can read down as well as I can to see that an AIS 6 has a very different implication. We're talking of severe brain damage. These AIS scores exist across the biomechanics world, and so if we're looking at rib injury, for example, or thoracic injury, AIS 1 is a single rib fracture. AIS 2 increments to a more severe impact, and so a more severe injury. We can continue down to look at pneumothorax, which is air being trapped within the thorax. Bilateral flail chest is a severe injury that's causing severe damage to both sides of the thorax. Soft tissue, we can apply this to heart if we want to get a measure of the severity of injury in the heart, from a relatively minor contusion through to laceration of the aorta, the largest vessel associated with the heart, and associated hemorrhaging to that as well. So we have an ability to grade the severity of injury. And this is a useful table and a useful system to categorize the major injuries, and it's typically reported as AIS. And so in papers where they're talking about injury, it might be that they're only interested in AIS 4 and above, looking at head injuries, for example. And so that's the kind of injuries that they're including in their study. For us, we look at the head, and the head has a series of different metrics that are used to try and measure injury. And whilst these are absolutely relevant anatomical or clinical definitions, from a biomechanical perspective, there's no numbers associated with it. And so if it comes back to this kind of scenario, and we're looking at concussions, then we can say that studies proposed by World Rugby, looking at rugby union, are going to review AIS 1 and above, which is useful from a clinical perspective because there's an immediate correlation to what AIS 1 and above is, but from our point of view, trying to generate an engineering solution that resolves that problem needs more data. And so we have a series of measures that measure in an engineering perspective a factor that is likely to be underpinning the severity of the head injury that you get. And there are a number of measures that have been proposed, typically from US-based research institutions. And perhaps the most common is the head injury criterion, abbreviated as HIC. And what that does is effectively plot the area under the acceleration time curve. So what we're saying with this plot, and this plot is this put into pictures, what we are saying is that if we were to imagine that our player was held by their feet and here's their head, and we're dropping them onto a surface, that there will be a time that we can measure if there's an instrument within this to measure the deceleration. There's an element of time that we can measure, and there is an element of acceleration, or in reality we're considering this to be deceleration, that we're interested in too. Now imagine if you had an older brother at home who decided it would be great fun to pick you up by your legs and drop you on your bed. Then the reality is that you would be probably okay so long as you haven't got a particularly tall brother, because you would hit the mattress would deform, and your head would slow down over a relatively extended period of time. And so that impact would look something like this. That is that you would slow down over a period of time. You go from some initial velocity to a final velocity of 0. But if your brother held you from exactly the same height, so the initial velocity is the same, you're still going to stop. The final velocity is the same. But he decided to drop you on this floor here, a tiled floor, then you're going to come to a stop far faster. So your deceleration or acceleration is going to be a lot greater. That is what this plot is describing here. And from an engineering point of view, we can use acceleration as a measure that is in some way meaningful to correlate back to these. So that's what we're after. These are what our end user recognize and operate with. Our clinicians, who ultimately work that we do is typically aimed at, this is what they operate within. They understand this. This is their language. But that's of limited value to us, because if you do an FE model, it's never going to turn out an answer that says concussion or severe brain damage. We need some kind of mechanism to translate what clinicians use into a language that we as engineers can understand and interact with. Acceleration suddenly becomes a parameter that we're familiar with, a parameter that our typical investigative techniques give back to us. What we do to make sure it's a fair comparison is that we take a window within the acceleration time trace to ensure that we're being systematic. And you would say typically that you're using HIC of 15 or HIC of 36, which means that you're effectively taking a window around the peak to include 15 milliseconds or 36 milliseconds. If your HIC, if your area under the curve comes up as being 400, then we have a 20% risk of mild traumatic brain injury or concussion. And so suddenly, we have an ability to link what our clinicians, our end users, value in terms of terminology and metrics to what we can do as well. We can't say absolutely that's always going to happen, but we can say there's a 20% likelihood of the interaction that I've just simulated in FEA, which will give us perhaps an acceleration time trace of this or this. Because it gets a hic of 400, there's a 20% risk of mild traumatic brain injury. Equally, if your hic is a lot higher, then the risk is more severe. We're making a bit of a jump between getting a number out of here and an associated risk. Unfortunately, people have done this correlation before, and the picture's not particularly good. On the bottom here, we've got hic. On the side here, risk of life-threatening brain injury. And so if we get to 1,000 hic, 16%. If we get to 2,500 hic, 99% risk. And so suddenly these measures are becoming very meaningful. And we can get blinded by this being almost the answer to all of our questions. There is, however, a limitation. The likelihood of your big brother holding you by your legs and dropping you head first perhaps isn't all that unrealistic. But in terms of the interactions that we are trying to model as engineers, the likelihood of a two-wheeler or a sports person or any other interaction involving someone taking you off your bike and dropping you head first is unlikely. This measure only works in terms of the vertical deceleration of your head. So that is presuming that you literally fall head first. In reality, of course, you're more likely to do something like that. And so you have a horizontal and vertical component, i.e., that your head and in particular the brain, which is what we're trying to protect, has some element of rotation as well. So there is a vertical displacement of the brain, but there's also a rotation as well. The significance of rotation is only relatively new from a biomechanical perspective. We've only recently appreciated that's probably the most injurious of the two mechanisms that you can get. A rotational injury is more likely to cause injury than a comparable vertical injury. One of the issues, however, is these correlations were developed in the 70s, where the range of experimentation that could be performed was more liberal than what it is today. And so to a certain extent, we are bound by these correlations. They're not wrong. They're just not fully accurate in terms of describing the rotational element, or they don't consider at all the rotational element of a head injury. But hic, or a derivation of hic, or a similar variety of hic, is what's used at the minute by the leading industries, because that is an accepted measure of head injury risk. We recognize there are limitations to it, but there's no other solution that's really been proposed at this stage. So we can look at road traffic collisions, RTCs. And we can use what we call a crash test dummy. So a plastic replica of a human. We can put them in vehicles and we can deliberately force a collision, so that we can do this ethically, of course. A hybrid 3 is one of the most up-to-date and most fidelic, lifelike dummy that you can get your hands on. And you can use it as a measure of subdural hematoma. So that's a level of AIS. You can then start to assess the effectiveness of preventing injury in a certain environment. So you could assess the ability of a car to protect the occupants against injury, or a particular design feature of a road. How effective is that at protecting the occupants from injury? And so a small female, a mid-sized male, and a large male, all strapped into a car, and children as well. And it has been used to correlate or define a threshold for certain types of injury, subdural hematoma. And so from these kind of studies, we know that if our HIC exceeds 779 in a small female, then there is a risk of subdural hematoma. And these kind of studies continue to develop the understanding that we have of injury. But in different parts of the body, different injury metrics exist. And this is off to a bit of a tangent from heads, but there's great value in appreciating that it's not only a head injury criterion that exists. This is the viscous criterion. And it's a method for measuring injury in the chest and the thorax. It's important and different from HIC because it begins to represent the viscoelastic properties of the material. And that's to say that this is velocity of deformation increasing in meters per second, getting up to 100 meters per second. This is the amount of compression that the tissue can withstand before injury. And so at relatively slow loads, you can compress the thoracic tissue to about 35%. Indeed, 34%, and if you were to believe this entirely, 34%, you're not going to cause injury at all. 35% compression, that's quite a lot of compression on the thorax, and you're going to start causing injury by crushing. So 35% compression you can get in the thorax if you were to do it slowly before injury. However, if we increase that rate, the velocity of deformation, to 20 meters per second, we can see that after only 5% compression, you enter a risk of injury. Faster still, less than 1% of compression, and you're going to get injury via blast. And so these metrics recognize that the body is very different in how it responds at different velocities. And so if you're designing military vehicles and you're concerned about thoracic injury in military vehicles, you need to be aware that you're dealing with compression tolerances of about 1%, and beyond that, your occupants are likely to get injured. That's very different than if you're looking at perhaps more manual interventions, CPR, for example, where you compress the chest when the heart has stopped. That's performed at a far slower velocity of deformation, and so that can achieve substantial chest deformation before you are at risk of crushing injury. And we can plot this against the probability of AIS. Your VC max, or your viscous criterion value. And you can see that as it increases, the probability of achieving AIS4 or above in the thorax increases. And so much like our linear correlation that we had with HIC, here we've got a correlation between an engineering measure, the viscous criterion, and a measure that is meaningful to clinicians. This is our interpreter. This is very much your ability to speak a different language and so converse with the people that you're trying to indirectly assist, the clinician. And these kind of translators exist for a number of other injury metrics as well. This converts an engineering measure into a clinically meaningful term. But there comes a point where we're limited by how we can push forward this subject. I inferred that a lot of the data that we're using and interpreting is from decades previous. It was then more straightforward to do tests that are ethically challenging, but biomechanically highly valuable. It's become increasingly demanding or increasingly challenging to get access to the material that will enable us to understand better things like the correlation between rotation and translation of the brain, which in itself creates questions and opportunities for engineers. Can we use emerging manufacturing technologies, 3D printing or additive manufacturing, to increase the database, the reservoir of data that is enabling us to understand injury? Here is this polymer-based person, a hybrid 3 dummy, and these are things that have sat in cars and crashed into each other, full of instrumentation, accelerometers all over the place, so that it can measure what's happening in the pseudo head. And that's been validated versus data from decades previous to make sure that the responses we're getting are reasonably accurate. We're seeing emerging computational solutions. Madamo is an example whereby you can effectively have a computational hybrid 3 and you can crash it into other things to replicate injury. But can we start using the ability of AM to design new and innovative testing methods? So this is similar to the workflow we were talking about yesterday. CT data rather, not micro CT, CT data of a skull. And using the software packages that are used in orthopedics, whereby you can demarcate different regions of the body based on the image intensity, you can start to see, and this is an infant because the blue areas are the fontanelles, the ligamentous structures between the bony plates that haven't yet fused fully. By using that software and adopting a workflow similar to what is used in orthopedics, we've taken some clinical images. We have segmented these different regions of the skull. We've then used a manufacturing technique that is relatively new. This manufacturing technique allows us to have different materials built within the same assembly. And so, whilst the black area is obviously different because it's black and not white, and so we can see that geometrically it's similar to the CT-derived image. Mechanically, this black area is different as well, different to the white area. Turn it round and the plate on the back is different again. And we've tried to match the mechanical parameters or the mechanical response of these different materials, both to the literature. And so studies on animals and humans have said this region of the brain, of the skull, has a certain property. This region has a different property. And the region on the back has a different property again. So we take our literature-based data, take our geometry or our anatomy, and then work with emerging 3D printing technology such that we can find or define materials that are able to give mechanically similar parameters to what we're after, and we can have the whole lot built. And so this picture hidden behind here is in essence what the inside of a hybrid 3 dummy looks like. It is a lump of aluminium covered with a skin-like layer. Go and look at any facility that tests other kind of helmets, and they use literally a lump of metal in a head shape. So they're trying to fine-tune the performance of vital safety equipment using a lump of metal. We think, and we don't think it's an unreasonable assumption, to say that if we were to have a higher resolution model, i.e. a model that has better representation of the performance of each of those structures, then we're going to get higher quality data out. Here, for example, we have an image of our skull covered with a layer of silicon. So we're getting some kind of coverage that is not hugely dissimilar to the properties of the skin. And then we go and drop it. We cover it with a layer of white and black dots. So white background, black dots. So we use our DIC technology we described earlier. The string there is a wire. So there is instrumentation embedded within our skull. And we go and drop it from 60 centimeters. So not hugely high. And we record it with high-speed video. And this was the first time that the extent of deformation within a skull has ever really been proposed. We can see that from the initial point of contact or impact, our head form retains a similar geometry to what it was built as. Go to the most extreme position, and we're looking at a substantial deformation. And so it would seem quite reasonable that combining emerging technologies such as polyjet, multiple jetting of different materials in one additively manufactured assembly can offer great value in terms of understanding the fundamentals of head injury and brain injury that can ultimately be applied to sporting contexts that are perhaps less relevant in this part of the world than others. But the fundamental science and research is applicable anywhere. This is an area that we're beginning to get involved in, but it's a huge area that can continue to be exploited by others. And so to recap on our unkind brother scenario, where we have a deforming surface versus a hard surface, this was a hard surface. We got substantial deformation of the head instead. The softer of the two interactions or the two surfaces at any given interaction will end up deforming. And that deformation then links back to these measures, which we can convert to be of clinical value. And we can appreciate that different acceleration time plots correlate to different injury severity. So we have fundamentally an understanding of the circumstance that we're trying to mitigate against. Now we're going to look at how we can start engineering solutions that might reduce that risk of injury. How can we take our acceleration time curve and squash it? We need to be careful that we don't extend it too much, because by the time we take our window of 15 milliseconds, if there's a massive extension to this, then we might end up with the same area under the curve as you do a very sharp impact. And so we always need to be conscious of the fundamental measure that we're applying. This is a child cycle helmet. There's a 2D CAD representation of what it looks like inside. You'll see that it has an outer layer that looks great fun for a kid, racing cars and all sorts, and we would go into a cycling shop and there would be 30 different designs of a cycling helmet for kids. The only real differentiation is the color and the animation on the side. A marketing tool that doesn't, at this level, achieve any functional value. Strip off that blue cover, and this is the shape of the underlying structure, made of expanded polystyrene. And we can see that at a relatively modest impact, kinetic energy is half mv squared, so at a relatively modest impact, we get a relatively steep, relatively severe acceleration that's measured when we have a metallic head and accelerometer embedded within our helmet. And our task is, can we find a way of flattening that out? Can we find a way of reducing the peak acceleration, but not extending massively the time duration, such that when we take our 15 millisecond window, the area under here has been lessened when we look at our own innovative solutions. And we'll just talk about some of our earlier work before we have a break. Jitendra and I were discussing yesterday, when looking around various sites, of the value of topology optimization. And he would probably struggle to recognize this as topology optimization at all, because it's our very naive attempt at doing so. Our skill at Cardiff is in additive manufacturing. So we can pretty much build in plastics, in polymers, whatever structure you want, given the expertise we have of tuning the machine and tuning the design orientation. And so we can design these and we can physically fabricate them to test as well. This started as a fairly basic shape that, as you can see, was warped. And actually CADing a curvature in 2D and then a curvature going in the third dimension is really quite demanding. And that in itself was quite a useful exercise for our students to go through. And you start with a very nominal structure, kind of a square that you extrude, that you curve to fit what looks like a head form. And then you get to a stage where you can manufacture it and impact it. These were actually impacted using FEA. And you get a plot, the blue one in this instance. Looks moderately promising. And so where do you go from there? And that's one of the problems that additive manufacturing gives you. is that in essence, you can create whatever you want out of a relatively narrow band of materials. That band is gaining greater width. But if you get a result from here using your nominal square that was extruded to a cube, how do you know what you do next? And that is where our very crude optimization method was implemented. And if you're being perhaps slightly less generous, you would say it wasn't an optimization system at all. It was systematically guessing as to what to do next. And so we thought, OK, let's see what happens if we knock out some of those interim struts. So rather than having a 2x3, we'll go for just one cube instead to make a dramatic difference, relatively dramatic difference. And let's see what happens. We go from the blue line to the yellow line. And at this point, we'll stop because it immediately became apparent that we needed to link back to some objective function. What are we trying to achieve? We have an ability, in essence, to go round and round in circles. We can change this. We can take more away. We can add more material. We can start to angle these struts. We can have all kinds of permutations that additive manufacturing affords us to do. But if we weren't careful, we could come up with structure after structure after structure, FEA it, manufacture it and test it. And this could happen indefinitely, because there would always be a different angle to align the struts. There would always be a different orientation to extrude in. We've started working with crystallographers from chemistry because they have a huge database of crystal structures where atoms are arranged relative to one another. Can we start designing the orientation of these structures to, in some way, mimic the anatomic structure of a material that we see to be favorable? And so this is our challenge, or this was our challenge. And we felt we needed to go back to basics, in this instance, back to Wednesday, try and get a better appreciation of what we're trying to resolve, and then come up with a novel engineering solution. Any questions so far? Yes. Yes. You're exactly right. Let me go back to something like that. So if you go to if we were to kind of time travel back to the UK, and if you were a designer or an inventor at home who made their own helmet, you would go along to an institute, a research institute, and you would want them to test how good your new helmet was. And they would take your helmet, and they would put it on something that looks very much like this, with an accelerometer on it. They would lift it up, and they would drop it. And if the acceleration in the accelerometer was below a certain threshold, your product would be considered good enough to sell. If your product was above that threshold, i.e. if the number was too high, your product isn't good enough to sell. And that's it. That's as close currently as we get to having a biomechanically relevant testing protocol. So they don't even go through the calculation of Hick. They look at solely the peak G, the highest number within the acceleration time trace that you get. And that is considered sufficient to determine whether a product is effective or not. Everyone recognizing it's highly oversimplistic, but there is a general hesitation to try and develop anything that is more advanced than that. Panels, certainly in the UK, that meet to decide the methodology to follow to assess a new design. Those panels consist of neuroscientists, and so they clearly have a very good understanding of the brain. They consist of bioengineers, such as us, who understand the relationship between a neuroscientist and actually achieving some numerical data. They comprise companies who has an entire product range based on testing of these, and so are, one would imagine, naturally quite resistant to change, because all of their other products might become redundant. They have people that test, so independent people that run the tests. And it's then down to that meeting to try and come up with a compromise that is suitable for everybody. So how do you get to a situation where everybody around the table agrees on something? And I guess what's not highly uncommon is that you almost end up with everyone reaching the lowest possible technology solution that they're happy with. And you end up with this, and this has been around for years, decades. And occasionally you might subtly adjust the threshold, but very rarely, indeed, I dare say never, has fundamentally the test protocol been changed. And so your question of how do you relate this to our head is absolutely relevant. In reality, people just, not just, but people add in accelerometers, not even rotational accelerometers really, just a triaxial accelerometer, perform a drop, and would pick out the peak acceleration and compare that to a threshold of yes or no. That's right. That's right. And so that's where we come back to things like this. And so people say that you wear a helmet, and the engineering construction of a helmet allows it to operate in effectively one environment only. A lot of these helmets, if not all, are made out of foam. So foam is a material that will crush and absorb energy very effectively, but can only operate within a very tight range of energies. If your energy isn't high enough, and by coincidence there'll be some foam lying around, but there isn't, but if your energy isn't high enough, then nothing will happen to your foam. If your energy is too high, your foam will squash and it won't achieve any functionality at all. If you loaded it with just the right load, then it will compress and it will give you a comfy landing. But the element of being too low and too high is quite narrow. There's only a very small time or small load that you can compress a foam by, and it achieves the function that you want it to. So that narrow performance window of the material means that we have to target when the foam is going to be active to a particular type of injury scenario. And that's to say that you can have a very low density foam if you want to protect yourself from a relatively low energy environment, which is absolutely a good thing to do. But that means that if you have that helmet on in a higher impact environment, it won't do anything because the foam will squash and there'll be no energy absorption. So where you're at greater risk, to say that if you're cycling, if you're on your bicycle and you just fell off because of a pothole in the road, you would have a low energy collision with the ground, and a low density foam would absorb that energy. In reality, that collision with the ground wouldn't be hugely injurious anyway. And it's nice that your helmet has protected you. And so you would probably come out of that scenario with no injury as opposed to a relatively minor injury, so that there is benefit. The trouble is if, whilst on your bicycle wearing that same helmet, you get struck by a car where the energy is a lot harder or a lot greater, then that low density foam would squash fully during that interaction. So it would absorb very little energy and offer you very little protection. And so you would have high energies being imparted onto your brain, and yet your helmet doing nothing to absorb any of that energy at all. And so that means that designers face a question or a problem. Do you design your helmet to protect you against falling off with a pothole or falling off for interactions with a car? And I guess most people would reasonably aim for the more extreme of the two, because that's where the greatest benefit would lie. And so trying to link that back into your question. So this is what we use to test. We test materials that we think are going to be effective in a very prescribed energy interaction. In reality, what's the likelihood of that energy interaction from happening when you're wearing your helmet? Probably quite small. How accurate is this at modeling your head? Probably quite small as well. And so our abilities currently to be effective at coming up with novel solutions for head and brain protection is inherently quite limited. And so that's what we'll go on to talk about later on. We've kind of said we would love it if we can get to this stage. But as we prompted yesterday, this technology is expensive, a lot more expensive than having one of those built that sits on the shelf for 15, 20 years. These models fractured because of the extent of deformation they went through. And so you spend $1,000 having one of these manufactured, you do one impact, you need another one. This can test successful and unsuccessful designs, and it can be put back on the shelf and used again next time. There's no risk of damaging that, or very, very little risk of damaging it. And so it comes down ultimately to an economic decision as well. If we were prepared to invest in this kind of technology to test our helmets, then we would get far higher resolution in terms of the outcomes that we're looking at. At the minute, we're only prepared to invest in this. And as a consequence, if you use a blunt instrument to measure the effect of your engineering solution, then you're only going to get an incremental change in technology afterwards. Anything else? We'll come on to that later on. There's a few slides where we look at the consequence on the brain to impact. And so we'll probably cover it within those few slides later on. OK, I guess I encourage people to have a 2-minute break or a 5-minute chunk of fresh air, and then we'll start again in 5 minutes or so. Thank you.